Hello, everybody. This is Group 4. My name is Brooke Worku, and here with me are my group members, Yangzong Doma and Ritsekingdo. We will kick off our presentation with a quick outline of what we'll be discussing on today. So we'll start with an introduction where we'll talk about the significance of our project and goals of our project. Then we'll proceed to the related work section where we'll talk about other similar studies that have been done in the past on the same subject and how our project differs and what kind of gap we're trying to fill in. Then we'll move on to the meats of our project where we'll talk about the details of our implementation. Under implementation, we'll discuss our system design, data cleaning process, algorithms used in our model, and rationale behind choosing our two best algorithms to implement from scratch. Then we'll proceed to our conclusion and future work section where we will be briefly wrapping up our findings and mention a few options for possible future works. Finally, we'll close off our presentation with a quick demo of our web application system. So, the use of data mining models for predicting future values have been a game-changing concept for a while now. The ability of such models to predict and extract meaningful outputs from raw input data has been critical, especially in the housing market. Various research and studies have explicitly stated that the fluctuations in house prices are a cause for huge concerns amongst house owners and buyers in the housing market. According to Australia's famous newsletter Urban Developer, with people's living standard progressively improving around the world and the effects of COVID-19 slowly diminishing, the demand for housing has been back at a constant climb in most metropolitan cities of Australia, especially Melbourne. It doesn't come as a surprise that various stakeholders interested in Melbourne's housing market would want to make their housing purchases and investment decisions from a very well-informed perspective. As such, the team and I set out to utilize data mining tools to explore the housing market in Melbourne. The primary goals of our project could be broken down into 3 points. Firstly, we'll explore the performance of 3 different algorithms used to predict housing prices in Melbourne. The 3 algorithms used in our work are linear regression, decision tree regression, and gradient boosting. To compare the performances, an experiment was carried out using built-in R functions. Then the best 2 algorithms were implemented by the team from ground up without using any built-in functions. Finally, our goal is to also present an interactive web application that runs our best algorithm in the backend. This web application will take in new housing features from the user and present a predicted price based on the input back to the user. Next, Yangzong will be talking about related works.
Several studies have been done on the same subject. I'm going to talk about 3 such studies and explain how our work differs and what kind of gap is filled with this paper. The first related work that we found was a survey from 2020 to find housing attributes that affected housing prices. It was found that these attributes are primarily locational and structural. Using their findings, we have used locational and structural attributes to train our model. While we also attempted to forecast housing prices using historical data, our work differs from the survey in a few ways. Firstly, we have selected a set of 3 prediction models, namely linear regression, decision tree regression, and gradient boosting model. We compared the performance of these models and chose the best one among them in our web application. Similarly, in 2018, a study on housing price prediction using machine learning algorithms was done to analyze historical housing data in Melbourne City. While this study has experimented with different models like stepwise and support vector machines, our paper initially conducts a comparative study amongst the aforementioned models. The last related work that I'd like to talk about is a study on real estate price prediction using machine learning. The study used algorithms like hedonic regression, artificial neural networks, AdaBoost, etc. The models were implemented using existing advanced data mining tools like Weka, RapidMiner, etc. However, in our case, we have refrained from using these existing tools and packages in implementing 2 selected models. Next, we're going to talk about implementation.
As stated in the introduction section, one of our chief goals in this project is to build a software application that users can interact with. This final web-based application was built using Shiny. Shiny is an R package that is widely used in both the industry and academia world to develop a simple and production-ready applications. So our Shiny application consists of two major functions, the UI function and the server function. The UI function is responsible for displaying the input boxes and general appearance of the application for the clients. It is this function that provides users the ability to interact with the application in a graphical manner. On the other hand, the server function consists of our predictive model. This function acts as the back end of the system. It has two parameters, input and output. The input parameter is used to pass in the user input data to the server function for further processing. It is through the input parameter that the server gains access to the user provided data. Conversely, the output parameter contains the output object that is meant to be rendered back to the client. In our case, the price predicted from our model will be kept in the output object and then provided back to the user in the UI. Once the UI and the server function have been successfully defined, the application will be ready to be served to the client via a local IP address and port number. The figure here in the slide sums up the design of the system in a very illustrative manner. As we can see from the figure, the client interacts with the application using the user interface provided by the UI function of the Shiny app. Once input has been collected, the UI function passes it to the server function via the input parameter. Upon receiving the input data, the server function will run the customized linear regression model on it to estimate a predicted price. Once the predicted price is evaluated, the app sends it as an output using the output parameter provided in the server function. It is the same output that will be presented in the client's user interface as the final predicted result. This is the UI of our system, just for your references. And next, Ritzek will be talking about the data preparation process.
So in the data preparation process, we're going to talk about the data description and the source. We also talk about the dealing with missing values and feature engineering. The dataset we use is the Melbourne housing market dataset from Google, published by Tony Pino in 2016. The dataset contains 34,857 records of 21 features. As we can see from the sample data, the features are the suburb, the address of the house, the number of the room, the types, the price in Australian dollars, and so on. Next, we talk about dealing with missing values, because our data has a lot of missing values with different features. We didn't want to delete all those missing values that would leave us only a small data set to work with our model. So we decided to use min imputation technique to fill the missing value for the numerical value. And then we use mode imputation technique to fill the missing value for the category values. We also decided to delete missing value for the price feature because it doesn't make sense to impute to fill those missing value for the level that we want to predict. Feature engineering. In this feature engineering, we decided to remove some attributes that are irrelevant to the model or can be substituted by other variables. For example, the feature suburb, address, postcode, latitude, longitude, all refer to the locations, which can be replaced by region name and concept area. We also create new features such as age and log price, because such as age and log price, the age we subtract the current year 2021 by the year built, and the log price we use the log function to do the log price. That is because yield build and price are a variable that span several order of magnitude, which may potentially affect the performance of our model adversely. We also use the correlation plot to find the degree of correlation between numerical attributes. As shown in the table, we can see that rooms and bedroom to have a really high degree of correlation, which mean that it's a redundancies and one of them can be removed to improve the calculation of the model. We also factor the categorical value into factor level because the model can only understand the factor level, not the category value. And it's also easier for us to implement the algorithm from scratch. Here is the snapshot of the final data after we clean and do some feature engineering. Next, we're going to talk about the model decision and how we come up with the model and explaining the model. The three models that we're choosing are linear regression, decision tree, and gradient boosting. First, I'm going to talk about linear regression, which the one I implemented. Linear regression is also known as a linear model. That is the model like assume the linear relationship between input variables and single output variables. The output variable can be computed using the input variables. There's two types of linear regression: a single regression and multiple regressions. In our case, we use multiple regression because we have multiple features. Regression can be written as a form of y equal to beta dot x plus e, where y is a vector of output, x is a metric of input features, and beta is a vector of parameter that we want to estimate, which means the coefficient, and e is the error term. In this linear regression, I use closed form least square solution, which can be derived as beta equal to the inverse of x transpose dot x dot x transpose dot y. And when we find this beta, which is the coefficient, we can predict the price by using the input metric dot beta.
The other model that we have selected to focus on in this study is decision tree regression. The reason we decided to explore on decision tree is primarily because it is non-parametric. This means that it can deal with large, complicated data sets without putting any restrictions due to parametric structure. In this slide, I'll be introducing decision tree regression. To do so, let's first talk about decision tree. The main idea is to split a complex decision into simpler ones. This is carried out by following a top-down approach in which a binary decision is made at each node to separate the classes until the leaf node. In a decision tree, two types of variables are used, namely predictor variable and target variable. The features of data are referred to as predictor variables, and the class to be classified is called the target variable. When the target variables are continuous, it is referred to as decision tree regression. Since housing prices are measured on a continuous scale, we decided to use decision tree regression for our data mining task.
Gradient boosting. Gradient boosting is a complex iterative algorithm known to build powerful predictive models. It is a supervised learning algorithm used for classification and prediction. So since our data mining task in this project is prediction, we thought of exploring gradient boosting. The algorithm is known to be one of the complex algorithms to easily understand. I'll try my best to briefly describe the working of the algorithm as follows. So first off, the algorithm takes in 3 arguments. Firstly, a training data set must be fed into the model. This data set must include the independent feature and dependent label data, which in our case is price. Secondly, the algorithm must be provided with a loss function. This loss function may be different for different data mining tasks. Since in our case, again, so we're dealing with prediction, the most appropriate loss function would, for example, be the mean square error. Thirdly, the algorithm needs to be provided with how many decision trees we would want to build to predict the next residual. For the sake of description, we can denote the number of decision trees to be built as M, for instance. So M would need to be provided as an input to this algorithm. So the first step in the algorithm is to initialize a base model with a constant value. The aim is to find a gamma value such that the loss value here is minimal. To find the gamma, we'll need to perform the first order derivative on the expression shown right here. This gamma value that we're going to be calculating and we're going to be obtaining is going to be the same for all the records in the training set, meaning that if some sort of training data set input is provided to this base model, it will be outputting a constant gamma value for all our records. So proceeding to the second step, we'll find a loop that iterates from 1 to m, where m again denotes the number of decision trees that we would want to build for our gradient boosting model. So for each iteration, we'll be computing the pseudo residuals using the equation here. So after obtaining the residual values for each data record, the algorithm proceeds to train a weak learner, which for instance could be a decision tree regressor, where the independent variable, which is the input to this decision tree regressor, would be the features, the housing features for our case, and the dependent variable would not be price, but the residual. So once we pass in this feature and get the residual, we multiply the residual retrieved from the decision tree model and multiply it with the learning rate to avoid overfitting. Usually the residual value obtained from such decision trees suffers from overfitting. So by multiplying it with the learning rate, the residual will be sort of normalized. The learning rate is, as you can see here, it is denoted with h of x. It is usually a floating number that ranges from 0 to 1. So once the residual is multiplied with the learning rate, we update our model. We will update our model. Yes, updated our model. So f of x here in the algorithm denotes that predicted output. So for every iteration, we keep on updating this f of x so that we get sort of new results for every decision tree build. So the more decision tree we build, the more residuals we obtain, and the closer we get in terms of the predicted output f of x. Once our iteration is over, the last updated f of x will be returned as the final predicted output of this algorithm.
Okay, so part of this project is we use 3 algorithms and use data mining tool to experiment and choose the best tool to implement from scratch. We use built-in function in ARM programming language to run all 3 models, and we split 75% of the data into training and 25% into testing. We evaluate the result based on the time complexity and the accuracy of training and testing for the 3 model. So the result from the experiment show here is that from the figure on the left show the error of training and testing of the 3 models. As we can see, linear regression has the lowest error of training and testing, while gradient boosting has the highest error of training and testing. On the figure on the right show the runtime of training and testing for the 3 models. It interestingly shows that the linear regression runtime of training and testing is really small, whereas the the runtime of training and testing for the grade boosting is really high. That is because of the high complexity of grade boosting that we just described before. From these two results of these two figures, we concluded that we decided to choose linear regression and decision tree to implement from scratch for this project. And then we're going to evaluate the result of these both algorithms.
In this slide, I'm going to talk on the results obtained from implementing linear regression. As you can see in figure 4, it shows the results of training and testing error for linear regression implemented from scratch versus using built-in functions. As you can see from table 4, training and testing of linear regression are almost identical, the error. With this, we can say that our implementation of the algorithm from scratch implies that our model is not overfitting nor underfitting. Another insight we found from our linear regression model is the coefficient of predictors. This table shows that rooms has the highest positive coefficient value, which means that a change in rooms variable may have the most positive impact on the value of the output. Therefore, we can conclude that rooms and council area are the two most impactful features for our predictive model. Here, when it comes to decision tree regression, the final decision tree regression model is presented as in the slide. It shows that type is the root node, which means that it provides the best split of the data. Upon comparing error produced between the implementation of decision tree regression from scratch versus using built-in functions, it is found that the error rate is the same between the two different implementations based on the construction of the tree model. So now I'm going to talk on the conclusion and future work. To conclude, in this study, firstly, we performed data processing. During this stage, we dealt with missing values using mean and mode imputation technique. Rows with missing price attributes were removed from the data set as part of data processing. Once data processing was fully completed, we proceeded to the experiment phase. We were able to prove that the linear regression algorithm performed much better compared to the other two. The performance was measured based on algorithm runtime and mean squared error. On the other hand, we witnessed that the gradient boosting algorithm performed relatively poor as compared to the other two. The decision tree regression models seem to fit in between the two extremes. We implemented the best two algorithms from scratch. Finally, we built a shiny web app using linear regression as our back-end model. Well, for future work, we could assess more on complex models such as neural network and deep learning to implement from ground up. These models have proven to show higher accuracy in their prediction output. Another addition for future work could be focused on adding more features to the dataset before training the model. Our model was trained using 10 housing features. It is our assumption that if more features were present in the dataset, the model and prediction output would have been even better. Next, Berg is going to show a demo of our application.
So when running our model, it is very important to note that all the inputs are supposed to be of numeric data type. So users will need to refer to the tables that are shown here in this slide to find the corresponding unique ID of each categorical variable. These tables will always be presented to the users for reference purposes when inputting their housing data. So for instance, we can now assume the role of the user and input the housing features and see what our predicted price would be. We hit make prediction, and there we go. We get our output. So the server runs the linear regression model based on these new input data, and we can now say that the price would be around 1,025,706 Australian dollars for this input. Thank you.